Hello everyone. We'll start with module number 4, which is Orifice, mouthpiece, and notches and wears. I can tell that it is fairly simpler module wherein you have to study a couple of derivations and then a bit of a theory and very simple problems in this particular module. One has to take care and then study because it is quite simple. Okay, the syllabus is like this: orifice and mouthpiece in this introduction, classification, flow through orifice, hydraulic coefficients, and then problems on that, numerical problems on that. Mouthpiece, what is a mouthpiece? Classification, and what is Borda's mouthpiece, and no problems, no numerical problems on that particular bit. Then you got a second part of the module 4 as notches and wears, wherein we'll be studying introduction, classification, and other type of notches and wears. Okay, first of all, we'll concentrate orifice and mouthpieces. So orifice is an opening. You can just see here that it is an opening in a vessel through which the liquid flows out, is known as orifice. So here I have shown a sketch in which there is a tank and there is a water standing there, and here there is an opening. The water is going out in the form of a jet. There is a specific shape for the jet, slightly exaggerated in its view, right? So here water will be going through this opening and then going out as a jet. So that is known as orifice. This opening is known as orifice. An opening in a vessel through which the liquid flows out is known as orifice. This hole or opening is called an orifice so long as the level of the liquid on the upstream side is above the top of the orifice. Obviously, the liquid level has to be above this. If the liquid level comes below, it will not be orifice, it will be a notch, right? Slightly exaggerated manner, if I have to explain, if the opening, the front opening, which is having a dimension something like that, if I exaggerated, water level is there, right? And then what happens is the water will be ejecting out. Now, as long as the water level is above this particular top level of the opening, then this is called as orifice, right? Of course, depending upon the size, that is the diameter of the opening, and then how high the water is or liquid is standing above this opening, helps you in classifying this as a small orifice or big orifice. But if the water level comes below like that, right, this will not be orifice, this will be a notch or a cut, right? So you have to understand this difference. So this is notch, which is second part of module number 4, wherein there is an opening and then water is coming out through some opening like that with the water level below the opening, right? Here in this case what happens is the opening is there and then level of water will be quite above that. You can just see here so much of water is standing, and because of that pressure the water will be coming out as a jet. Okay, the purpose of an orifice is the measurement of discharge or to empty the vessel. Now, depending upon what is the data that we can get about the orifice, means the diameter of the orifice and how high the water is standing above the orifice, this helps you in finding out how much is the discharge, at what rate the discharge is going out. And one more direct purpose would be just to empty the tank, right? Why the opening is provided? Just to take the water or liquid out, right? If you have kept oil, if you want to take it out, every time going on the top and then opening the lid and then taking the liquid in some container would be a problem. So you put an opening and then allow the liquid to go out. So that is the purpose. An orifice may be provided in vertical side of a vessel or in the base, but the former one is more common in the sense you can provide this opening at the base also. Even then also it is orifice, but generally that we find orifices are provided with the opening on the vertical face so that jet ejects like that. That is a common one, that is what is said. Okay, here the same figure is there. What is that we have to observe in this figure is I have written what is known as vena contracta. In earlier figure also I have written that vena contracta. Here if you just look at the geometry of the jet that is coming out, because of the pressure from the top, because of the pressure from the bottom, when the jet comes out, it will be decreasing in its diameter and reaches the minimum, and then afterwards again the jet diameter increases. I think you will be able to appreciate this. Generally it is a sharp crusted opening like that, right? Here also on this side also there is an opening something like this. When water comes out, it will be having a curvature something like that, and then it goes out that way. Here also it ejects like this, means there is somewhere the z diameter reduces and then reaches a minimum, and then afterwards it enlarges in its size. So water when it comes, right, maybe direct, maybe from here, obviously it will be having a tendency. Because of that tendency, the decrease in the diameter happens, and the least diameter section is known as vena contracta. Approximately the position of this with respect to the opening will be d by 2, means if diameter of the opening is d, this is roughly d by 2 is the position of vena contracta, right? So I have told that it is at section 3. Section 2 is exactly the opening, 1 is somewhere there inside. Okay, here classification is based on geometry of the opening, maybe circular, rectangular, square, or triangular. Openings may be there, but most common one would be the circular one. The orifice can have any geometry, it's just an opening, right? Now here in the second kind of classification, you can just see here H. What is H? Capital H is indicating the head, it is called head, above the orifice, means from the center of the orifice up to the free surface of the liquid. This is H, and if this H is more than 5 times the diameter is diameter of the opening, 5 times D, then it is a small orifice. And if H is greater than 5 times D, H is greater than 5, not greater than 5 times D, then it is big orifice. In the sense, when H is large enough compared to this diameter, then it is small orifice, and that's what we are going to study in detail. And if H is becoming less and less, the H is comparatively less with respect to the diameter, means H is less than 5 times diameter, then it is a big orifice. The formula for that will be slightly different. Okay, here big and small orifice classification we have done in the second part. Now the third one, depending upon shape of upstream edge. Just now I have shown sharp edged orifice, there is bell-mouthed orifice also, right? What is meant by sharp edged orifice? Here I have shown these edges. You can even look at the figure also, my sketch, wherein a very small contact of the edge is there when the jet comes out. Here also I have shown a beveled edge, and then the jet when it comes out, it will be having a very small area of contact with respect to the opening, right? Now if we put an opening, if I tell the thickness of the opening as something like that, and then bottom opening as something like that. And if the water flows now, obviously it will be gradually flowing and then coming out, gradually flowing, touching everywhere and then coming out. So this is bell-mouthed, right? Bell-mouthed orifice. Right here, obviously, because the water or the liquid is in contact with a lot of surface of the opening, then there will be losses, or head will be lost, right? In sharp edged orifice, there will be least contact with the water, right? If it is cut like that, you know that hardly there is any contact left, and because of that the head loss will be less when the water comes out. It affects what is known as C with a suffix D. You are going to study that. CD is nothing but coefficient of discharge. This will be quite large in case of sharp edged orifice, quite large, and then in bell-mouthed orifice this CD will be less because energy lost will be more. Okay, now fourth classification, discharging conditions. It's a free discharge and partially or fully submerged or drowned. Now here the opening is there. I'll try to draw it here. There is an opening here, and then inside liquid, if it comes below, then it is no more of orifice. Already I have told you, right? So what can happen is, this is large enough, but on the downstream side here, if the water level is there and then the water is coming out, it is a free jet, freely discharging type, right? By chance on the downstream side, on this side, if the liquid has risen up and then covered part of orifice, means part of orifice is covered, even though there is a head over here, it is not coming out freely, right? Part of it is submerged. Or even on the downstream side, if the water level goes up to that point, then what happens is, because this difference, obviously the discharge will be there, but the thing is, because it is completely submerged inside, it will be behaving slightly in a different manner. So that's why that kind of orifices are called partially or fully submerged or drowned orifices. Okay. Now types of orifices I have listed. Anyway, here also there is a list, but here orifice can be of different types depending upon their size, shape and the nature of the discharge, but the following are important from the subject point of view. Already I have listed up, but anyway, here in the notes how it is given, I'll just show you. According to the size, it can be small or large orifice. I have told you, here it is there, right? H is greater than 5 times D, H is not greater than 5 times D, that will be big. Then you got according to the shape, circular, rectangular, triangular orifices. According to the shape of edge, that is sharp edged, we have discussed this, or it is bell mouthed. According to the nature of discharge, discharging free or fully submerged or partially submerged orifice, right? So I have explained you this. The same thing is listed out over here. Okay, now what is vena contracta? So when the jet comes out, I have told you it decreases in its diameter, comes to a minimum, and then slightly they diverge, and the jet goes, if I consider this itself, the jet goes that way, right? So all this will be a water which will be coming out. Now the jet will be not of the same size of the opening, it decreases in its size and reaches a minimum size. So at one vena contracta, number of properties are written. You can just go through. Number one, the liquid flowing through the orifice forms a jet of liquid whose area of cross section goes on decreasing, and at section CC the area is minimum. This section is approximately at a distance of half the diameter of the orifice. At this section, that is vena contracta, at this section, the streamlines are straight and parallel to each other and perpendicular to the plane of the orifice. If the plane of the orifice is vertical, then obviously the streamlines will be perfectly horizontal at the vena contracta. This section is called vena contracta. Beyond this section, the jet diverges and it is attracted in the downward direction by gravity. I have shown them in the red lines. Okay, so that is about vena contracta. There are a number of points that you can remember. To account for loss of energy, actual velocity will be slightly less. So it will be Cv into root 2 gh, and Cv is called coefficient of velocity. It is of the order of 0.95 to 0.99. Okay. Then AC, that is area at vena contracta, is equal to a coefficient of contraction Cc multiplied by A naught, area of the orifice. Area of the orifice is simple, pi d squared by 4, but because at vena contracta it will be slightly less, there is a multiplier Cc. It is called coefficient of contraction. So actual discharge will be the area of flow, cross-sectional area of the flow, multiplied by velocity of the flow, actual velocity, Cv root 2 gh. So A naught into root 2 gh multiplied by Cc into Cv. This Cc into Cv is replaced by Cd, which is known as coefficient of discharge. This is an important factor, and this will be of the order of 0.6 to 0.63, in that range it will be there. This will be Q actual, right? Q theoretical, if you want, it will be A naught root 2 gh, actual area of the opening, and theoretical velocity is root 2 gh. Because of that, A naught root 2 gh would be theoretical discharge, right? And Cd will be a multiplier with which, if you multiply to Q theoretical, you will be getting Q actual, right? Then Cc theoretical value is pi divided by pi plus 2, that is 0.64 to 0.65. Coefficient of resistance Cr, because we know now coefficient of velocity Cv, coefficient of contraction Cc, coefficient of discharge, coefficient of resistance. So Cr is equal to 1 by Cv squared minus 1, or theoretical kinetic energy, V theoretical squared by 2g, not kinetic energy actually, it is a velocity head, right? So theoretical velocity head minus actual velocity head divided by actual velocity head, right? So this ratio will be 1 divided by Cv squared minus 1. So that is called coefficient of resistance. Now hydraulic coefficient, whatever Cc, Cd, Cv, Cr, they are there. The same thing I have listed out systematically here. The following 4 coefficients are known as hydraulic coefficients or orifice coefficients. All of them put together, they are called hydraulic coefficients. First one, coefficient of contraction Cc. The ratio of area of the jet at vena contracta to the area of the orifice is known as coefficient of contraction. So Cc equal to area of the jet at vena contracta divided by area of orifice. The average value of Cc would be 0.64. Coefficient of velocity, the ratio of actual velocity of the jet at vena contracta to the theoretical velocity is known as coefficient of velocity. The theoretical velocity of discharge V will be equal to root 2 gh. Cv will be actual velocity of the jet at vena contracta divided by the theoretical velocity V, and this becomes root 2 GH divided by, no, something has gone wrong. I shouldn't have written this here. Root 2 GH is not there, right? So it is the actual velocity of the jet at V naught contractor divided by V, which is given by theoretical velocity actually. It should be, and theoretical velocity is root 2 GH. Okay, the difference between the velocities is due to friction of the orifice. Okay. Coefficient of discharge. This is ratio of actual discharge through an orifice to the theoretical discharge. I have stated this earlier also. Q actual A divided by Q theoretical, Q TH suffix. This ratio is less than 1, and this is known as CD, coefficient of discharge. CD is actual discharge divided by theoretical discharge. CD will be actual velocity into actual area divided by theoretical velocity into theoretical area. So that comes out to be CV into CC. An average coefficient of discharge varies from 0.6 to 0.64. That is what is hydraulic coefficient. The fourth one is coefficient of resistance. Already I have told about that. Okay. Now discharge through the orifice. Okay, this is a mathematical application for the discharge expression. Consider a tank fitted with circular orifice in one of its sides as shown. Let H be the head above the center of the orifice. I'm sorry. Okay. Now consider 2 points 1 and 2 as shown in the figure. Point 1 is inside the tank and 2 at V naught contracta. Let the flow be steady and at a constant head of H. Now applying Bernoulli's equation between 1 and 2, what we can apply? So P1 by rho g, that is P1 by gamma plus V1 squared by 2g plus Z1 equal to P2 by gamma is rho g, V2 squared by 2g plus Z2. But because 1 and 2 are at the same level, Z1 and Z2 are same. If you take there itself, it is 0, 0. If you take anywhere else as a horizontal reference, both of them are at the same level. Because of that, the Z1 becomes Z2, that is 1. Because of that, it will be, expression will be this way. Now what is pressure at 1? It is P1 by gamma is nothing but H, and velocity V1 squared by 2g is 0 because it's not moving or moving with a very slow velocity, right? Now P2 by gamma, because when it comes out it will not be having any head, it is 0 atmospheric pressure. Therefore V1 is a very small in comparison to V2, as the area of tank is very large compared to the area of the jet. So if I substitute all this, what happens? You can just see here, it becomes H plus 0 equal to 0 plus V2 squared by 2z. From this it will be got that V2 is root 2gh. This is expression for theoretical velocity. V2 is equal to square root of 2gh. Okay, supply of water is continuously made into a tank so that there is no change as far as H is concerned. Right, center of orifice. This arrangement is to calculate hydraulic coefficients, right? We'll see experimental determination of hydraulic coefficients. You've got a big tank in which the head over the opening, over the orifice, is held constant by supplying extra discharge. There will be overflow arrangement also, so that whatever extra water that will be added will be going out, otherwise it will be going through the orifice. And then the z that is coming out will be measured for its geometry of horizontal distance and then vertical drop. So how much it has gone down, how much it has gone horizontally, this x and y are measured, so that we can calculate CV, coefficient of velocity. Okay, anyway, we'll see it in detail. Determination of CD. Now how do you find CD? Water is allowed to flow through orifice fitted to a tank under a constant head H as shown in figure. The water is collected in the measuring tank for this is a measuring tank. We have collected water for a duration of time t. The height of water in measuring tank is noted. Now this is noted down, right? Something like, let us say, some y, not y, not h. What shall we call it as? We'll call it as L, right? So this height for which the water is collected is, say, L, right? This particular height. Then actual discharge through the orifice, Q actual, will be equal to area of measuring tank. Means if this has got some dimension like that, and then the tank is there, so what is the base area? That area of the measuring tank is that. Means suppose if you have got measuring tank length as breadth and width, right, B and W on the other side, right, this perpendicular to the board W, parallel to the board is BW, that is area of the base into height of the water in measuring tank. Height of the water in measuring tank we have collected L, divided by time is T. So it will be WBL, right? That is the volume collected divided by time. That gives you actual discharge. Theoretical discharge is Q theoretical, which is equal to area of orifice into root 2 GH. So this will be equal to A into root 2 GH. Okay, because area of the orifice is A, root 2 GH is a theoretical velocity. Now CD becomes Q actual divided by A into root 2 GH. A is the actual area of the opening, root 2 GH theoretical velocity, actual discharge. This helps you in finding out CD. Okay, then CD is already done. We have done this. Determination of coefficients of orifice. Okay, here I have found coefficient of velocity also and coefficient of contraction also. We'll go through this. Coefficient of velocity CV. There are number of methods: z distance method, velocity measurement method, right? Momentum method. So here we have considered the jet distance method, as in this figure also x and y. Here this is vena contracta, the position CC is at vena contracta, this point is vena contracta. So as if the jet goes horizontally x distance, it is falling down through y. Horizontal velocity, if I consider it as v, the distance moved in time t is vt, right, any general arbitrary time. Y will be equal to ut plus half gt squared. U is initial velocity, vertically it has got 0, half gt squared. Now common from this both is t. If you get rid of t, you will be getting y equal to half g, and then t is x by v, x squared by v squared. Now if you simplify for v, you can just see here g x squared divided by 2y, that is the actual velocity. Okay, but Phi actual divided by V theoretical is CV. So that's why phi actual divided by V theoretical. If I put both the expressions, V actual is square root of gx squared divided by 2y, and theoretical velocity is square root of 2gh. Now if you simplify both of these, Cv will be equal to x squared divided by 4yh, or it is Cv is equal to x divided by square root of 4yh, or 2 root yh. So that is the expression for Cv. Okay, the same thing is directly given. X is horizontal distance traveled, y is vertical distance between P and CC, P and not CC but actual center of the orifice. Determination of CC, CD equal to CV into CC. We have found CV from here on the right hand side, and from the left hand side we have found CD also. So we know CD, we know CV. So only unknown in this expression is CC. It can be found. Okay, a couple of problems we shall have. In performing an experiment to determine different coefficients of sharp-edged orifice, a jet of water issuing horizontally from the orifice is 25 mm diameter under a constant head of 150 centimeters, fell through 0.9 meters vertically and struck the ground at a distance 2.3 meters horizontally from vena contracta. The time required to discharge 91 liters of water was found to be 53 seconds. Calculate all the coefficients of orifice. Okay. Okay, CV is equal to x divided by 2 root yh. Just now we have root or derived, and we have here x. How much is x? X is 2.3 meters because jet has gone through a distance of 2.3, and corresponding vertical distance is 0.9. So I have to put for y 0.9, for x 2.3. This h is 1.5 meters. It is given. Substitute and simplify. You will be getting CV as 0.9898. Now Q is equal to 91 liters divided by 53 seconds, because it is said that 91 liters of water was collected in 53 seconds. So discharge rate would be 91 liters divided by 53 seconds. 91 liters, if I want to convert into meter cube, you have to multiply by 10 raised to minus 3 and divide by 53. I will be getting 1.717 or 1.72 10 raised to minus 3 meter cube per second. Okay. Now Q is given by CD A root 2 GH. Actual cross-sectional area A is pi d squared by 4. Root 2 GH is theoretical velocity. Now if you compare these two velocities and calculate what is the value of CD, you will be getting value of CD, the coefficient of discharge. It has come out to be 0.645, but CD equal to CC into CV, that's why CC will be 0.651. Okay, this is problem number 2. So second problem, oil flows through 25 mm diameter orifice under a head of 5.5. This is H. This is D. At a rate of 3 liters per second, the jet strikes a wall 1.5 meter away and 120 mm vertically below the center line of contracted Z. Okay. Calculate the coefficients of velocity, contraction and discharge. Okay. Straightforward problem. H is equal to 5.5, X is 1.5, Y is 0.12 meters. CV is X divided by 2 root YH or under root 4 YH. Substitute, CV comes out. Q equal to CD A root 2 GH. Q is given 3 liters per second, 3 into 10 raised to minus 3 meter cube per second. CD as it is A 0.25 diameter, 0.025 for meter diameter. So pi d squared by 4 into root 2 GH. Substituting 0.588 or 0.59 would be CD value. Now using CD equal to CV into CC, you can calculate CC as 0.637. Okay, all the three coefficients are found. Okay, here slightly a different problem. A 4 cm diameter orifice in the vertical side of a tank discharges water. The water surface in the tank is constant 2 meters above the center line. If the head loss in the orifice is 0.2 meters and the coefficient of contraction can be assumed to be 0.63, estimate the values of coefficient of velocity, coefficient of discharge, the discharge through the orifice in the location of point of impact of the joint, a jet on a horizontal plane located 0.5 meters below the center of the orifice. Means y is given as 0.5. How much is x? That is what is asked. Okay, now looking at the data, I can start with ideal velocity or theoretical velocities phi root 2 gh, already given all the values. H is equal to 2 meters because that becomes 6.264. Head loss HL will be nothing but H, the original one, minus velocity VA squared by 2g. If you do this, we'll be getting head loss, and this is given to be 0.2 meters directly. So I'll equate this to 0.2 so that I'll be getting velocity actual will be equal to V 9.81, and then in the bracket it is 2 minus 0.2 because 2 is the overall, 0.2 is the head loss, so you'll be getting one value 5.943 meters. So that is actual velocity. Now coefficient of velocity is actual velocity to theoretical velocity, that is to say 0.949. Then coefficient of discharge CD will be CC into CV. So it comes out to be, CD comes out to be 0.598. Now the discharge through the orifice will be equal to Q equal to CD A root 2 GH. Substitute everything and simplify. We'll be getting 4.707 liter per second as the discharge. Okay. Now next is mouthpiece. What is a mouthpiece? Mouthpiece is a short tube of length not more than 2 or 3 times its diameter. Very important. If you attach a more length, it will be a pipe, but the length of the pipe has to be restricted to only 2 times diameter or 3 times the diameter, provided on a tank or a vessel containing fluid, such that it is an extension of orifice and through which also the fluid may discharge. Both orifice and mouthpiece are usually used for measuring the rate of flow or discharge. Now classification of mouthpiece. Number 1, based on position with respect to the tank or a vessel, which are fitted the vessel to the vessel that they are fitted. Now external mouthpiece attached externally, or it can be internal mouthpiece. There is a different name for internal mouthpiece, which is Boda's mouthpiece. Second classification based on shape, it can be cylindrical mouthpiece, it can be convergent mouthpiece, or it can be convergent divergent mouthpiece. So this is very important that you should know. So normal one will be having a inside shape will be perfectly like that, cylindrical mouthpiece. Convergent mouthpiece, the mouthpiece will be having a shape like that it will be, here it enters, and then when it comes out the diameter is slightly less. Convergent. Now convergent divergent, in this what happens is it converges first and then afterwards it will be enlarged. So like this, the mouthpiece will be having a inside shape will be something like that. So here it will be entry. So this is the convergent divergent. The flow gets in and you can observe that length of convergence will be slightly less and length of divergence will be a bit more, but this will be convergent divergent. So based on the shape, not the elevational shape, but you can just see here it is cylindrical convergent or convergent divergent. Okay. Now based on the nature of the discharge at the outlet of the mouthpiece, that is mouthpiece running full, then mouthpiece running free. Okay. The meaning is like this: mouthpiece running full in the sense when you have suppose there is a mouthpiece like that, and on this side you got a water standing, and when the water comes out, if it is touching the mouthpiece superficially and then it comes out like that with the equal to the area of the mouthpiece itself, it is running full. But mouthpiece running free, the jet is so sharp that it comes out like that without touching the mouthpiece. It just gets out without touching the surface of the mouthpiece. In that case, that is, if it comes like that, right, it jumps out like that, then it will be running free. Okay. Now flow through mouthpiece, again mathematical approach here. We'll see what it is, how it is done. There is an attachment of the mouthpiece, you can just see there, right? So actually speaking, there will be a vena contracta and then it comes out and then sudden expansion will be there. So here from CC to 11 there will be slight expansion in the size. The head above the mouthpiece is H. So consider tank having external cylindrical mouthpiece of cross-sectional area A1. A1 is the cross-sectional area. Attached to one of its sides, the jet of liquid entering the mouthpiece contracts to form vena contracta at CC here. Beyond this section, the jet again expands and fills the mouthpiece completely. Let H, the head of liquid above the center of the orifice, VC, velocity of liquid at cross section CC, AC, area of flow of vena contracta, V1, velocity of the flow at outlet at the external point, A1 is the area of the mouthpiece at vena contracta, not at area of the, A1 is the area of the flow. Here there is a mistake. Area of the orifice, area of the mouthpiece, that's all. Cc is coefficient of contraction. Now applying continuity equation at Cc and 1 1, AC into Vc, area into velocity equal to A1 V1. Because of that, Vc will be equal to A1 V1 by AC, right? AC this is. So AC by A1, if I write, that will be Cc. AC by A1 is nothing but Cc, coefficient of contraction. And taking CD equal to 0.62, we get AC equal to 0.62 by into A1, AC equal to. So VC becomes V1, so VC becomes V1 divided by 0.62. Of course, this is Cc, coefficient of contraction, if I take 0.62. Now the jet of liquid from the section Cc suddenly enlarges, and due to sudden expansion, there will be head loss HL, which will be given by Vc minus V1 whole squared by 2g. And substitute for Vc from this equation, right, and simplify everything, you will be getting head loss is equal to 0.371 V1 squared by 2g. This is head loss. Next, applying Bernoulli's equation at 1 1, right, and at point A, so PA by rho g, VA squared by 2g is ZA, P1 by rho g, V1 squared by 2g plus Z1 plus HL, that is the head loss. Now A and, now look at this point, A and 1, the external one, PA by rho g is atmospheric pressure, H, not atmospheric pressure, PA by rho g is equal to pressure head of H, right? PA squared by 2g is negligibly small, ZA is equal to Z1, ZA equal to Z1. Okay, now P1 by rho g, when it comes out, the atmospheric pressure is 0. V1 squared by 2z, HL is given by 0.375 V1 squared by 2z. From this I have brought that. From this, H equal to 1.375 V1 squared by 2g, or V1 is equal to root 2gh divided by 1.375, which gives you V1 as 0.855 root 2gh. Theoretical velocity of the liquid at outlet is 0. Not 0, square root of root 2, square root of 2gh. Coefficient of velocity for mouthpiece CV will be equal to actual velocity divided by theoretical velocity. So this is actual velocity considering contraction. Theoretical velocity is root 2gh. Because of that, CV becomes 0.855. So Cc for mouthpiece, if you take it as 1, as the area of the cross sectional of the jet of liquid at outlet is equal to area of the mouthpiece equal same. So thus CD becomes CV into Cc equal to 1 into 0.855. So 0.855 would be the CD for mouthpiece. Borda's mouthpiece, internal mouthpiece or a re-entrant mouthpiece. So the mouthpiece which is attached inside like that, a short cylindrical tube attached to an orifice in such a way that the tube projects inwards to the tank, inside the tank, is called Borda's mouthpiece or re-entrant mouthpiece or internal mouthpiece. Running free, if the length of the tube is equal to its diameter, the jet of the liquid comes out from the mouthpiece without touching the sides of the tube. In this it is shown like that. You can just see here in the figure. So it is running free, right? Discharge Q equal to 0.5 A root 2 GH. In running free condition, this is the formula where H is height of the liquid above the mouthpiece, A is the area of the mouthpiece. Rhoda's mouthpiece running full, so that is running full. You can just see here the length of the mouthpiece is slightly longer, not just one time the diameter. Then if the length of the tube is about 3 times the diameter, the jet comes out with its diameter equal to the diameter of the mouthpiece at outlet. That will be running full. So discharge in this case will be equal to Q equal to 0.707 A root 2 GH, where H is the head above the mouthpiece, A is the area of the mouthpiece. Okay, we'll not solve any problems on mouthpiece. Thank you. We'll stop it here.